Your code might be secure, but what about the 300 or 3000 dependencies you didn't write? Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios, and what I want to talk about today is supply chain attacks. So in such a way that developers can understand that. Developers, architects, technical leads. This is not a video for security specialists. This is a video for people building software or managing how software is developed. And I think this is a very important topic because supply chain attacks are on the rise, and they will continue to be on the rise because they are one of the easiest, or maybe not necessarily the easiest, but one of the highest leverage attacks. By just attacking one point, you can infect thousands, tens of thousands of different people. If you want, it's like poisoning the city water supply instead of breaking into each home to poison the water in that home. It's about attacks that can spread very, very quickly. And the recent example for this has been the Shai Hulud attack targeting NPM packages. And we are going to talk about this in a minute. First, let's just quickly define what a supply chain attack is and explain what it's about. Then I will give you some real-world examples, and then I will give you some ways to protect against these attacks. And I will also discuss a little bit about specifics for embedded systems. And we'll end up with a few conclusions. So let's start with a definition. As I said, a good metaphor is that supply chain attacks are like poisoning the city's water supply. The official definition would be something like supply chain attack is when an attacker compromises software not by targeting your code directly, but by poisoning something that you depend on. Library, a build tool, the operating system, the infrastructure that delivers your dependencies. And this works because you have, in modern software, a lot of dependencies. As an anecdote here, I used to complain about Maven when it first appeared, because when you run Maven the first time, it feels like it's downloading half the internet. But then NPM came about, and it seems like it's downloading all of the internet. So many different packages, and I can't help but wonder how many of those are vulnerable. Do we actually have control over that, or is just hopium that this is working? You have in your applications a lot of dependencies. Some of them are development tools, some of them are libraries, some of them are Docker containers, and all of these can be attacked. You can have compromised packages. Instead of downloading a package that is correct, maybe you are downloading another package that has a very similar name, or a name that's not visibly different. This is called typo squatting. So, for example, the letter A in Unicode in Cyrillic alphabet is the same as the letter A in Latin alphabet, which means that you could theoretically, and this happens occasionally, if you copy-paste the wrong thing when you install the package, you could install the wrong package and install a clone that is poisoned instead of installing the correct package. Um, Maybe the account of the maintainer for that package is compromised, and an attacker takes over and has an ability to sign and publish packages by adding some malware inside the code. Maybe the maintainer is malicious. There was a case that we documented also and commented on this channel where there was a situation of one maintainer being so overworked that he accepted the help and promoted to maintainer another person that contributed for months to a project. But then after they gained the maintainer status, they introduced malware in the package. So you cannot count necessarily that the maintainer wants the right thing, or at least that's the current reality in security. You cannot count that you are getting the right package. You cannot count that that account was not took over by somebody else. Then you have attacks based on build process compromise. So let's say you have a CI tool and that tool is compromised, or you have a plugin that you add to that tool and that plugin is compromised, or you are running a script that you downloaded from somewhere and that script is compromised. And sometimes they are compromised in very subtle ways, like downloading something that looks correct and then running it. There are so many ways to do supply chain attacks, and once you manage to do a supply chain attacks, it affects so many people at once. You could have plugins or extensions for your ID that are compromised, or if you are using Docker, which mostly everybody is today, you could have container images that are compromised, or operating system packages that are compromised. If you are working in embedded systems, you are used to taking a big library that contains the basic shell tools that you need and configure that, hopefully to reduce the attack surface to keep the minimum number of tools. But what if you are getting the wrong package and the one that you are getting is compromised? Or what if that package was compromised before and it contains certain poisoned tools? This is the reality of supply chain attacks. So now let's look at some real world examples. The most recent one is Shai Hulud, named after the Dune name. By the way, Dune is one of my favorite books, and on one hand I find the cultural references very appropriate. I wish it were for something less malicious, because Shai Hulud in Dune is both a figure for good and for bad, for power and for wisdom. It's a very interesting thing. So, what is Shai Hulud in the context of supply chain attacks? In September 2025, a self-replicating worm thread spread through NPM. When developers installed the infected packages, so you do npm install a package, that package was already infected, malicious code executing during the installation, and that code would scan for credentials, npm tokens, GitHub tokens, AWS keys. it used those stolen npm tokens to infect other packages that the developer maintained and publish new malicious versions. So this means it basically spread in a network, right? It started in one point, somebody a number of people downloaded that malicious version, and then their packages were compromised, and then the people who downloaded those packages had their own packages compromised, and so on. Each compromised developer became a distribution point. Within days, over 500 packages were compromised. The malware created public GitHub repositories to dump stolen credentials and push malicious workflows for persistence. So not only was it stealing and modifying packages, but also made some changes to the automation process so that it kept doing that. In November, we had Shai Hulud 2.0, more aggressive, and switched to pre-install scripts for wider reach. And it also added a destructive capability, blocked from spreading it to the attempt to wipe user data. So fun. Over 25,000 GitHub repositories were compromised with credentials publicly exposed. So, using packages as a weapon and as a vehicle to spread through to other packages. This is an example of why supply chain attacks can be so destructive. And by the way, we are talking about software supply chain attacks, but there's also an area about hardware supply chain attacks, like adding listening devices on processors that you install, or on cards, normal cards that you install in your computers. This is also possible. And often it's very difficult to make the difference because hardware designs change pretty fast these days, and it's easier to print those cards today than ever before. Now let's talk about a second example, which is SolarWinds, a compromise in the build process. In late 2019, Russian state-sponsored hackers infiltrated SolarWinds, a Texas-based company that provides IT infrastructure monitoring software. They gained access to SolarWinds build system. Between March and June 2020, the attackers injected malicious code called Sunburst into updates for SolarWinds Orion platform. This code was digitally signed with SolarWinds legitimate certificate, so it appeared completely trustworthy. When approximately 18,000 government agencies and private companies installed these routine security updates, they actually installed a backdoor. The malware was stealthy and selective. It would lie dormant, blending in with legitimate network monitoring traffic. The attackers only activated it for high-value targets. Major corporation, think tanks, at least 9 US federal agencies, including Treasury, Commerce, parts of the Department of Homeland Security. The breach wasn't discovered until December 2020, when the cybersecurity firm FireEye noticed suspicious activity in their own systems and traced it back to SolarWinds. By then, the attackers had maintained access for months, conducting espionage and stealing sensitive data. All right. So, build process, another way to do this. Imagine if what you are building gets modified by a malicious actor and then published to your clients. That's what this is about. And a third example is CodeCove, CI/CD tool compromise. In early 2021, attackers targeted CodeCove, a code coverage testing tool used by over 29,000 companies, including IBM, GoDaddy, and the Washington Post. The attack went undetected for 2 months. Attackers exploited an error in how CodeCove built their Docker images. Docker images are created in layers, and CodeCov had left a sensitive credential exposed in an intermediate layer of a publicly available image. The attackers extracted this credential from the Docker image. Using it, they modified CodeCov's bash uploader script, a script that thousands of companies automatically downloaded and ran in their CI/CD pipelines to upload test coverage reports. The modification was subtle. The attackers changed one line, replacing CodeCov's IP address with their own. Now, when customers ran the script in their CI environments in function normally, uploading coverage data to CodeCov as expected, but it also silently uploaded all environment variables to the attacker's servers. These environment variables contain exactly what attackers wanted: API keys, database credentials, cloud access tokens, and repository access credentials. The breach wasn't discovered until April 1st, when a customer noticed the script's hash didn't match what was listed on GitHub. By then, attackers had been harvesting credentials for 2 months. Federal investigators later confirmed that attackers used the stolen credentials to break hundreds of customer networks, specifically targeting software development companies and technology service providers. Companies like HashiCorp disclosed that their GPG signing keys had been exposed. Really bad. The true scope took months to unfold as victims discovered what credentials had been compromised. The attack demonstrated how CI/CD tools sit at a critical choke point. They have access to everything needed to build and deploy software, making them perfect targets for supply chain attacks. So, to recap, what happened is they managed to modify one script that uploaded test coverage data, and with a very subtle modification, just uploading to another IP, it uploaded the environment variables as well as test coverage data. And it looked like it was working perfectly fine, but actually they were harvesting credentials, because a lot of times the credentials are in environment variables. Once again, very, very effective attack. So with a very subtle change, starting from a very small mistake, we can get to the point where credentials for thousands of organizations are stolen and then used in who knows which ways. So these are 3 examples of supply chain attacks, and now let's talk about how we can prevent. Now, the basic idea here is we cannot trust packages, we cannot trust different versions of packages. So the only way we can trust a package is if it is a specific version and that version is audited, so it's proven or at least less likely to have security issues. And the only way to prove that is by installing that specific version, but not only based on its version, but based on its digital signature. Now, this can still lead to a few issues. Maybe an attacker stole the key and was able to introduce malicious code. But if you're using a specific version that is audited, and you know that you're using that version because you're using the cryptographic hash and you can pin it, then it's unlikely that you'll have any of those issues. And I realize this is a pain for developers, but this is kind of where we are. What we need to do is to validate, to make sure that we are using a trusted version, and in order to make sure we are using that trusted version, to make sure we are checking the hash, the cryptographic hash of that version. And based on that, to install. So that is basically what we need to do. Now there are other things that we can do. Dependency hygiene, so minimize audit and pin versions. We want to have as few dependencies as possible. The ones that you have need to be audited and pinned. In CI/CD, run all processes with least privilege. Very important, so that it cannot steal information. Use internal mirrors and proxies for packages. This is very common in large organizations, so you probably don't have this issue. Code review needs to extend to dependency change. So whenever you change, add a new dependency, modify a dependency to a newer version, you need to audit that package as well. Again, in large companies, this is usually done by security departments, hopefully. Now, how do you pin to specific versions and integrity hashes? You need to look at your tool. NPM, Maven, Gradle, they all have their ways of doing that. Python has its way of doing that, pip. And if you are using C++, depending on which tool for package management you are using, again, you need to check the hash. Now, when it comes to containers, if you are building a Docker container, they have mutable tags because, for example, the Docker tag Ubuntu latest is a label. The underlying container changes. So if somebody manages to take over and to publish a malicious version under this label, you are not protected. Because of this, you need to do pinning based on the hash, which sounds like from Ubuntu 24.10, I think it would be 24.02, whatever, at SHA 256, and then followed by the actual hash. And you can obtain this by running docker images -- digest. This will give you the correct hashes. And then you can automate part of this with Dependabot, Renovate. There are some tools. You can lint it with Heidolint. So there are tools that you can use in order to make this slightly easier. Now let's talk a little bit about tools and then a bit about embedded systems. As practical tools, you have certain tools that scan for dependencies. SNYK, SNYK, Dependabot, WASP dependency check. You should use a software bill of materials. This is a list of all the packages with their versions that are included in a Docker image or in a piece of software. There are tools for this, for containers. You have Trivi, you have Gripes. There are some tools that you can run and they give you the software bill of materials, and then you can also validate for known vulnerabilities each from time to time, periodically, ideally at every build, because new vulnerabilities can appear. And you can also do Docker file linting with Heidolint. But in general, the general idea is just audit, pin, and use cryptographic hashes to ensure that the correct version is used and that nobody replaced it without you knowing it. Let's talk a bit about embedded systems. Now, embedded systems are different in the sense that you are deploying the whole thing out in the wild. You need to assume that this is white box, so hackers can extract the firmware, because they usually can. They can either download it from your website, from your upload site, or they can extract it from the device. So then what you also have in addition, the issue of firmware updates, which the only way you can prevent this is by using some kind of secure booting. You need a secure chain for booting, a secure chain for updating. And if devices get compromised, you need to have a way of delisting devices and disallowing them from accessing your network, maybe disabling them if possible. And this requires a lot of digital signatures, with one of the signatures being stored on the device, ideally in a hardware security module. But yeah, who knows? I know those are expensive, and sometimes you need to do something else. But ideally, you'd have hardware security modules. Of course, with embedded systems, you also run the risk of hardware supply chain attacks, where, as we said, somebody adds a chip from the factory or intercepts a transport, adds some additional features that you don't really want to your hardware, and then sends all the data to their own servers. Those are harder to prevent. It's very, very difficult to figure out if the hardware component is legit or not. And that is a separate problem, fortunately for us developers. All right. So what do we need to do? We've learned all this about supply chain attacks. We've seen how effective they can be. We've seen that they can spread in a network, which is really scary. You can have network effects for attacks. And the only real protection we have is what we discussed. Audit, pin, check the cryptographic signature, and make sure that whenever you run specific programs, plugins, tools, first do all this, but also have the lowest privilege possible, in which these tools run, because otherwise you are facing a real chance of those tools being modified and having malicious content. And imagine what happens if somebody can extract your credentials for cloud, for GitHub, for Git repositories, for Docker, for the places where you publish packages. Just imagine that. That is a real problem for many organizations. So be very careful with this. This is not a thing to take lightly. On the other hand, part of it is infrastructure, and if you're working in a large company, part of it is with the security department. They will take care of auditing and so on. It's annoying for developers because when we want to install something new that would be very useful, maybe a library, maybe a plugin, maybe an ID, maybe a script, you get blocked by security until they manage to do their audit. But this is the world we live in, so we need to adapt to it. And remember, a big issue here is typo squatting. So be very careful what you copy paste from the internet, because some letters look the same in different alphabets, and you want to make the visual difference between them, but they represent actually different names, which means that you might install the wrong version of a package or of a script or of a tool, or you might be visiting the wrong URL, and be very careful with that. Right? What do you think about all this? Have you seen supply chain attacks in your line of work? How do you defend against those? Do you have any other questions about this? Let us know in the comments, or about any other types of attacks that you'd like to understand as a developer. Let us know in the comments. We love comments. Like, share, subscribe. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.